Polyacrylamide is a type of water-soluble polymer made by joining together acrylamide monomers. First, let's talk about what it is. Polyacrylamide can be synthesized into linear or cross-linked chains. It possesses an exceptionally high molecular weight, ranging from hundreds of thousands to tens of millions of grams per mole. There are three primary types: nonionic, anionic, and cationic. These variations are engineered by combining different monomers or by modifying the amide groups later to form carboxylate or quaternary ammonium salt functional groups. When polyacrylamide is introduced into water, the polymer chains exhibit distinct conformational changes, transitioning from coiled-up configurations to fully stretched-out structures. This behavior depends strictly on external factors: the ionic strength of the water, the pH level, and the overall electrical charge density. These parameters dictate how the polymer performs in aqueous environments. When dissolved, polyacrylamide forms a crystal-clear solution at low concentrations, but it quickly transforms into a thick, sticky, highly viscous solution at medium to high concentrations. Cross-linking reactions turn these linear chains into three-dimensional, hydrogalic structures akin to high-capacity sponges that hold massive amounts of water. Commercial product series are categorized by their molecular weight, intrinsic viscosity, and charge density or degree of molar substitution. Today, this versatile agent is heavily utilized in wastewater treatment, oil and gas production, papeterie manufacturing, mineral processing, textile finishing, and agricultural soil management. With these foundational principles established, we will now explore its practical mechanisms in water purification. Next up is everyday life. Water treatment. In the process of coagulation and flocculation, tiny suspended colloidal particles floating in water usually carry a negative electrical charge. Consequently, they push each other away. This electrostatic repulsion makes it incredibly difficult for them to clump together naturally. Cationic polyacrylamide, or a precisely selected anionic variant, dramatically reduces this repulsion through charge neutralization and bridging effects. The ultra-long polymer chains adsorb onto the surface of multiple particles simultaneously, connecting them to form larger, rapidly settling clumps called flocks. This adsorption process is driven by a combination of electrostatic attraction, hydrogen bonding, and van der Waals forces, all of which must achieve equilibrium with the hydrodynamic mixing energy of the water. The core principle behind bridging flocculation is that specific segments of the polymer chain attach irreversibly or quasi-irreversibly to the particle surfaces, creating extended loops and tails. These loops and tails reach out to capture neighboring particles. However, a critical boundary exists. If you add too much polymer, it can reverse the surface charge or completely coat the particles, preventing them from colliding. This disruptive phenomenon is known as to make strong, flexible, shear-resistant flocks and avoid overdosage, engineers must meticulously select the optimal polymer architecture, charge density, and molecular weight. Flocculation performance depends on several variables: the exact polymer dosage, the pH and ionic strength, which influence charge shielding and chain extension, the mixing energy and shear history, which dictate particle collision frequency and flock strength, and the critical contact time before settling. In highly saline water, the polymer chains inevitably shrink as the electrostatic shielding effect intensifies, which usually requires an adjustment of the dosage or a complete change of the polymer type. Furthermore, temperature fluctuations and the presence of inorganic coagulants will alter the operational window. The jar test serves as the universal laboratory standard to optimize this selection process. First, a rapid mixing phase spreads out the polymer. Second, a slow mixing phase promotes flock growth. And finally, a quiescent period allows for gravity sedimentation. Throughout the test, we track the reduction of turbidity over time, the clarity of the supernatant water on top, and the final volume of the settled sludge. In municipal clarification plants, a typical effective polymer dose ranges from merely 0.5 to 10 parts per million. Under optimized conditions, water cloudiness is cut down by more than 80%, leaving a compact sludge that is exceptionally easy to dewater. Next up is industry, oil and manufacturing. Inside high-velocity transport pipelines, very dilute, high molecular weight polyacrylamide acts as a powerful drag reducer in turbulent flow, or classic manifestation of the Tom's effect. The long polymer chains actively suppress the chaotic, turbulent structures near the pipe walls and weaken energy-wasting eddies, thereby lowering the pressure drop significantly for a given flow rate, depending on specific pipeline geometries and fluid characteristics, and provided the polymer maintains its mechanical integrity. A drag reduction of approximately 30% to 70% can be achieved. In hydraulic fracturing operations, friction reducer formulas deploy highly diluted polyacrylamide to minimize pumping pressure during the initial pad and slurry injection stages. Typical undocked fly dosages range from tens to hundreds of parts per million, carefully adjusted based on real-time water chemistry and propant sand loading. In specialized scenarios, higher dedicated dosages may be implemented. Mechanical shear degradation is strictly controlled by ensuring gentle mixing, properly inverting emulsions, and avoiding excessive recirculation within the pumps. For enhanced oil recovery, partially hydrolyzed polyacrylamide is added during water flooding to modify fluid viscosity and optimize the mobility ratio. This process dramatically improves the volumetric sweep efficiency across suitable oil reservoirs. Additionally, the polymer helps control fine migrations by binding dispersed solids together. Beyond the oil and gas sector, polyacrylamide improves fiber retention and drainage rates in the wet end of paper manufacturing, increases thickener throughput and overflow clarity in mining operations, and supports textile sizing. These industrial applications typically operate at modest parts per million dosages, resulting in a 5% to 20% increase in solid capture alongside significantly clearer filtrates. Finally, let's look at environmental, social, and governance criteria through sustainable agriculture. Cross-linked polyacrylamide networks form advanced capable of soaking up and retaining massive volumes of water, often reaching hundreds of times their dry weight before slowly releasing it as the surrounding soil dries out. When these hydrogels are incorporated directly into the plant root zone, they buffer moisture fluctuations, reduce evaporative water loss, and preserve essential soil-pore connectivity. Concurrently, linear polyacrylamide molecules, applied at very low concentrations, stabilize the aggregate structure of the soil and enhance water infiltration through fragile surface crusts. What we observe through empirical field data includes a substantial reduction in surface runoff, decreased soil particle detachment, lower tailwater turbidity, and a mitigation of nutrient leaching. While the exact scope of these reports varies based on soil classification, field slope, and rainfall intensity, proper management has verified a 20% to 60% reduction in soil erosion and runoff cloudiness. In modern drip or furrow irrigation systems, hydrogels successfully extend watering intervals and improve seedling survival rates under acute drought conditions. Safe utilization remains absolutely paramount. Commercial polyacrylamide products destined for environmental and drinking water applications are manufactured under strict industrial quality controls to limit residual acrylamide monomer content, typically keeping it below 0.05% by weight. Its application must strictly comply with local environmental and potable water regulations. Product selection, dosage determination, and field operations should always follow supplier specifications and comprehensive on-site risk assessments to ensure total regulatory compliance. To sum it all up, polyacrylamide's highly tunable molecular structure and adjustable electrical charge make it an exceptional tool for water clarification, pipeline drag reduction, viscosity control, industrial and soil moisture management. Executing this effectively requires a precise matching of the polymer traits with the water chemistry, the mechanical, shear environment, and the structural constraints of the process. And remember, always validate these molecular dynamics through laboratory jar tests or pilot scale evaluations before advancing to full-scale operations. Thanks for listening.